which we've been doing on that engine for a long time. I didn't know we could call it homogeneous charge compression. That's 14.6 to 1. That's the one that delivered, the one on the dyno is the one that delivered 38.8% thermal efficiency.
Yeah.
And this one delivered 37.5, and we started out at 29.4, they were 1.6 liter. But we've been doing it with that one. I just thought this is illegal. All of a sudden, on the cover of SAE magazine 3 months ago, Mazda does homogeneous charge compression ignition. You read it, and it's still got a spark plug, you know.
Yeah.
And so, but you know, that's. We had a guy call up to come down and do filming from SAE because he wanted, you know, since we're doing it also. At the time, he wanted to come down. I was just much too busy. But he said he's going to come back next year.
Yeah.
In any event, oh, the rest of the papers disappeared.
Those were Camille's, he left.
Pardon me?
Those were Camille's papers and he left. So
Oh, okay. Well, I've got it. Sneaky that I am, I also. And the thing to notice here is we start out, we make gasoline 2 different ways. Here's gasoline made from oil, and here's gasoline made from methanol. And the difference in the results in the exhaust gases can easily tell you which one it is. See, we've got a huge amount of here's from methanol to gasoline, from methanol to gasoline. In each case, we have a huge amount of methane, ethylene, ethane, acetylene. Those are all made from partially oxidized hydrocarbons. But this one has a lot of toluene, and we started out with a lot of toluene here. This one has a lot of 1,2,4-trimethylbenzene in it, and clearly there was almost none here. So this is the unburned hydrocarbons for the exhaust. It's unburned fuel, so it should look similar, with the exception we'll see a lot of low molecular weight molecules in the exhaust that we don't see in the original fuel, because these are molecules that are partially broken and then a hydrogen recombined on that carbon site, and that happens in the quench sites. So
there's a lot less concentration, I'm assuming, at the exhaust.
Pardon me?
These are not the same concentrations. Like, this does not represent the same amount.
No. These concentrations represent a percentage of the total.
Of the total.
But it's still the point you can see. If it's bigger, you have a larger percentage of the total, and if you had more in the fuel, you're going to have more in the exhaust gases. And then we got here. Here's different fuels have different flame speeds. These are the laminar flame speeds before you add turbulence. Turbulence can triple and quintuple this. Hydrogen is by far the fastest burning. The hydrogen molecule is simple. It doesn't have to go through a lot of chemical reactions to prepare it for the flame front, and so it goes very fast. Acetylene is a triple bonded olefin, and consequently not all that stable. You begin to heat it up and it starts to break apart again, so it's high. But gasoline and the rest of them are down here. Gasoline goes up maybe to about 100 centimeters per second. They all fall down in here.
Percent gas in air.
Pardon me?
The percent gas in the air?
Yeah. This is percent. Stoichiometric for hydrogen's here at 30. Stoichiometric for gasoline is down to several percent. You can balance the chemical equation.
Is that gas to air ratio?
Yeah.
Fuel to air ratio?
What percentage of gasoline, or whatever the gas is, we've got here, propane and butane, whatever the gas is.
Yeah.
What percentage of the mixture is that component?
volumetric.
And what happens is peak flame speed is always a little bit richer than stoichiometric, but you can calculate the stoichiometric for each of these and plot them on here if you want to. But the point is, all the things that we typically are going to be able to burn are down here, where our goal is going to be make them burn faster.
And that is volumetric, percent gas in air?
Yeah.
Because you said stoichiometric, so 1-to-1 is around 30 for hydrogen?
Yes.
Okay.
Yes. But hydrogen is the one fuel you can go much richer and still have an increase in flame speed.
Mm-hmm.
The hydrogen molecule diffuses rapidly. So you can end up, you can go to a very rich mixture and end up with a high flame speed. But the point I'm trying to make here is it can vary a lot, but the fuels that we're interested in are all slow enough laminar flame speed, so we're not be able to rely on the laminar flame speed to get a rapid enough delivery of energy to make the engine run. We're going to have to add some turbulence. During the intake stroke, we're going to add a lot. Now, as we get in after this test and begin to look at swirl and squish and a number of other things, we'll find ways that we can add a lot of turbulence and take a very lean mixture that's down here and move it up into a usable range. But that's further work changing the shape of the combustion chamber.
Dr. Smith, is there such thing as too much turbulence in the combustion chamber?
With hydrogen, there sure is.
With
The hydrogen combustion chamber that we used is the lowest possible, and at high load, we use a spark plug that's already over in the edge of the chamber to slow it down, and we still got some fluctuations. Well, at 8-to-1 compression ratio we didn't, but by 10-to-1 we were having a problem. So, but yes, for the hydrocarbons we typically use as fuel, we're trying to speed them up.
We haven't reached a point where we have too much turbulence with the hydrocarbons we're using for fuel, right?
Say again?
We haven't reached a point where we have too much turbulence with the hydrocarbons we're using for gasoline.
No. The problem is, as we add turbulence, we increase the heat transfer coefficient. So it's always a trade-off. What limits the amount of turbulence is heat transfer. In that 1.6 liter engine that did 37.5% brake thermal efficiency, there were load conditions in which, of the heating element of fuel, half of it went into the water jet. 37.5% went into actually running the engine, and that less small amount came out of the very cold exhaust. And so we have a swirl ratio there that is much higher than any production engine, because we want to run propane at an equivalence ratio of 0.6, lambda 1.6. We're going to take a stoichiometric mixture, get rid of 40% of the fuel, and still expect it to burn. We're end up with a very high ratio of specific heats because it's a low temperature, but how do you get it to burn fast? Well, we added a huge amount of swirl and squish, and finally we're able to accomplish that, but we pretty well hit the limit with that. That's why the next engine we built was a much higher compression ratio, which also makes the mixture burn more rapidly, and we have near sonic throttling intake valves, which is another way to do it. If the gases come in at the speed of sound, you've added a lot of small-scale turbulence that makes it burn a lot more rapidly. But we can discuss those after we have this test. This is a setup for the next 5 lectures are looking at different shaped combustion chambers, different types of intake systems, to try to make it possible to use a wider range of fuels over a wider range of fuel-air ratios. And then this just explains dissociation. And if you remember, when we started out, of the original things that decrease efficiency, one of them was dissociation, because it delays
energy release?
Yeah, it delays energy release. And you can see that when you're making a lot of carbon monoxide, you're making less carbon dioxide, so you didn't fully oxidize the fuel. You didn't use all the stored chemical energy in the fuel. If I take a carbon molecule and burn it to carbon monoxide, that's a lot less energy release than carbon dioxide. And so, see, here's the CO2. As the temperature goes up, which means in the peak temperatures in the cycle, when they have more and more equilibrium, is more and more carbon monoxide, less carbon dioxide. And the same thing, we're getting more and more diatomic hydrogen and free hydrogen and less HO2. So that means that as we get these very high temperatures, we're not releasing all the energy. Now, on the expansion stroke, when it begins to cool down, equilibrium pushes it back the other way. We go this way, and it tries to burn the fuel then. Unfortunately, we can't burn it all.
Temperature in the chamber?
Yeah. These are just bomb experiments here. We're taking a stoichiometric mixture of, well, for this case, this one's stoichiometric, this is rich, this is lean, of isooctane at 50 psi in a chamber, and we're raising the temperature and then seeing what the equilibrium concentrations of all these constituents are. As long as we're at low temperatures, basically it's nitrogen, water vapor, and carbon dioxide, just like our balanced equation. But as the temperature gets higher, things like the nitrogen and the oxygen that was in the fuel starts to form NO.
Yeah.
Because this is more stable at a high temperature than diatomic nitrogen or diatomic oxygen. And consequently, we don't get to release all the energy in the fuel, and that comes later on the expansion stroke, but rather inefficiently. And we end up finally with some NO in the exhaust.
Well, how about the CO, the carbon monoxide? How the higher temperature is the same principle?
Same exact thing. You can see as the temperature, here's the temperature range. As it goes up, we get more and more CO2, and this is a logarithmic scale, so this is very exponentialized. A little more temperature. Now, the CO2 it's much easier to complete the oxidation of the CO2 before the gases leave the chamber. unfortunately, turning NO back into diatomic nitrogen and diatomic oxygen takes weeks. So it also forming it is slow. So you never reach these high equilibrium concentrations, but whatever the peak temperature is, it kind of stays through the rest of it. So now you get in the catalyst, now we've got to reduce it in the catalyst somehow. That's why we can't run the engine lean, because if we put a little oxygen in there, any way we try to reduce it, we're just going to end up, all the catalytic agents are just going to oxidize stuff. So, but yeah, you can see here that when we run it lean, this is less of a problem. And this is equivalence ratio 0.8. We're running these engines at 0.6. The 1.6 liter is best efficiency at 0.6. You take it up to stoichiometric and it'll probably knock and destroy itself. Because it's 12.7 to 1 compression ratio. And of course that one is 14.6 compression ratio. So those engines, they're automobile engines. Actually, this one is a Miata cylinder block with a Kia cylinder head on it. We couldn't use the same cylinder head. To get the compression ratio up and to get the smaller valves we wanted for low RPM, we had to use a cylinder head from a different manufacturer. And that one over there has a Nissan block and a Nissan head, but they weren't originally designed to go together, and the block puts the water in on the wrong side of the block. The cylinder block has the flow of water from the water pump on the, if we look at it this way, right-hand side, but the cylinder head expected it on the left-hand side. So one complete master's thesis was figuring out how to, he did a CFD model of the water flow in the block and figured out how to solve the hot spot that had occurred in the back of the left-hand side of the block because it expected to get the water there. That was his master's thesis. When he got hired at Chrysler, he moved right into management. So they were those are the problems that really cause a lot of concern at an automobile company. You know, if what you want to do is build high-performance engines, they got to do it to prove they're technically astute, but you don't get as high a pay there because there's too many people that just want to do it for free. You know, you get in, I mean, it's so much fun that it doesn't pay as much. Yeah. And whereas when you go like my PhD student into emissions, then you get paid top dollar because it's real important. But the more fun the stuff is, the less money you make at it. You go work for a racing team, you're going to get paid half of what you get paid in Detroit. So there again, you're back to deciding what do I want to do to have fun, and what do I want to do to make money. And if you spend all your time just trying to make money, you'll end up wishing you hadn't. I'm sure of that. I've seen it happen too many times. But in any event, that's about it. Then this won't be on the test. We just got started for the 5-valve engine, the whys and the where nots. But this is really, we'll go through this for the next test. Yeah. I can hand these out again. I'll make enough copies of this before. And that's about it. And of course, this you've seen. This is just we're mechanical engineers. Now, are there questions? Anything that we got all the sheets here. If there's any questions, remember of the 6 differences in between our idealized calculations and the real world, have a good understanding of where they occur and why, because that's the fundamental thing that we're trying to get across in this portion of the course. These last 5 lectures, we need to know the relationship in between the theoretical analysis that we started out with and the real world. And then in the next 5 lectures, we're going to take examples of engines and look at how they went about solving those problems. Yeah. And most of the time, as you begin to fix one, another one gets worse. It's always a trade-off. You know, there's nothing. Now, with homogeneous charge compression ignition, of course, the time losses go to 0. If you do it all top dead center. Yeah. The heat losses, when you don't have knock, you can insulate the chamber. It's expensive, but you can insulate the chamber so that you reduce the heat losses because you don't have to worry about knock. Yeah. If I insulate any of these chambers, all I'm doing is increasing the temperature of the in-gases and it knocks worse. So we can get rid of a lot of the heat losses. Blowdown is, as I said, maybe a 2% loss. We already have 4-valve heads that'll drop that down to 1%, but it's only at peak loads. As you go to the lighter loads, it becomes more diminished if you have variable cam timing, which we do.
So because you cannot open the exhaust valve in a 0 second. It takes
Yeah,
time.
exactly. So down at the
Does it have
bottom,
mass?
you can't put the corners on the right-hand side of the work loop.
Yeah.
When that's the bigger volume side.
It takes
Yeah.
time.
And then disassociation, we're just gonna have to live with it, but once again, it's a small component.
Can you explain that again, why it happens?
Well,
energy.
as you go to higher and higher temperatures, you cannot oxidize all the fuel immediately. But the part you can't oxidize is 1% or so, 2%. It causes problems with emissions because it makes NOx, but it's not a big, it doesn't hurt the efficiency a lot. So if homogeneous charge eventually is supposed to be for lean mixtures, in which case, you know, we get
could
to,
oxidize because you have oxygen.
So, you know, but right now, you know, we're not just trying to extend the lean limit monstrously. But disassociation is there, but it's not a big component. Even when it does occur, we haven't lost a lot of efficiency. And so, and friction is a big problem, but friction is mainly handled by figuring out how to make the rings seal the cylinder wall without a lot of pressure. To put this in the cylinder bore, I have to squeeze these down, and then as I let them go, they start putting pressure on the cylinder wall, and when the pressure from the combustion comes down, it gets behind the ring and pushes it out even more. So the more force I have to put on the rings against the cylinder wall, the more friction. The big component is of friction is the rings. About 3/4 of the friction in the engine is in the cylinder block, and most of that is in the rings and the piston. So it's design of, I wish I had some newer pistons, but you know, these are high performance, so you can't see. But newer pistons are getting much smaller. The rings are getting much thinner. We have gone from 1972 to 1995, we reduced the friction of the ring and piston package by about a third. And I don't have any good numbers from my own data for recently how much that's changed, but I know it's continued to go down. And but you know, friction's friction, and you know, that's always going to be in it. But if you can get it down to where it's a very small value. At full load, friction's less than 2%. You know, I mean, it's not a lot. It's a problem at light loads because the friction is not a strong function of the load in the engine. The rings still drag about the same whether they're at high pressure or not. Once they get up on the oil film, then the drag is reduced. But the piston has to be moving for the ring to get up on the oil film or the skirt to get up on the oil film. Without any motion, the rings just break through, touch the metal, and then you got a lot of friction. That happens at top dead center and bottom dead center. When it happens at top dead center and high pressure, you get more wear. So if I look at a cylinder bore on a very worn engine, I have a perfectly straight part at the top that is the original bore because the ring never got that high. Here's the head gasket surface. The top of the block's here. When the piston's at top dead center, the top ring is still below that. So that top part's no, and then I get a bunch of wear, and then it tapers down less. And but that's, you know, friction is. Do you want to use roller bearings? We can get the friction out completely of the crank and everything. We use roller bearings. These are all journals. High friction, cheap bearing. Very inexpensive. It's just a piece of metal here. This goes around the journal and we put some oil in between it.
Don't you have the oil film in between the piston?
Yeah, all that lubricates this is an oil film in between this bearing surface and the crank journal.
And there would be less friction if you have a bearing than the
A
oil
roller
film
bearing,
itself?
yeah, a roller bearing is a lot less friction. It's just, you don't oil it then. You know, you add a lot of oil to a roller bearing and it gets worse. But you don't have the problem, you know, in a roller bearing with friction. If you have no oil here, it goes immediately.
Yeah.
But no, there's a lot that we can do, but it costs money. And that means what we need is other vehicles to compare it to that are expensive. And we're beginning to get that. We're beginning to get that.
So if you had bearings, that means you could idle at a much lower RPM then?
The RPM limit now is mostly emissions. As you go very low flow rates, you begin to lose heat in the catalyst. So when they stop at 800, if you go back in the 60s, we idled at 500, 600 RPM, no problem.
It's about
But
the same.
at that point, we weren't worried about emissions. Now today with emissions, you have to pull it up 800 or 900 to keep enough heat to keep the catalyst from cooling down too much and stopping the function. So it's an emission problem that prevents us. We can, with variable valve timing, we can idle at 450. That engine there, the starter motor cranks it at 400 RPM. You crank it at 400 RPM, and you're pulling air only in. and you've got the throttle open just about enough for maybe maximum 800 to 1,000 RPM. You start putting fuel in, and it just comes up to 500 RPM. The Bendix is not disengaging the starter motor. You go up like 650, it disengages, you can run back down to 400, no problem at all, just smooth as ice. But that has near-sonic throttling intake valves, and you couldn't do it without those intake valves. We will cover that topic in the 5 lectures that follow this list.
Why do you only open the throttle a little bit for starting it?
You don't need it's nice to have, remember when throttle's only open a little bit, you're adding a lot of turbulence. If you have a manifold vacuum that's less than half an atmosphere, the gas going by the throttle plates is reaching about the speed of sound. So you'd like to add a lot of turbulence. At this point, you know, you're not worried about power. So you might as well add more turbulence, and then you add the fuel in. In this case, we add the fuel in before it goes by the throttle plates, so everything ends up very well mixed.
Because I know that if you're trying to start a carbureted engine, you try to like choke it with your hand to like.
Yeah, well, what you're doing in a carbureted engine, the fuel enters just because there's a line up to a venturi, and the faster the air in the venturi, so it's just being sucked in. Oh, you put your hand in the carburetor, now it's really being sucked in, so you can get it rich real quick. It's just like closing the choke. And but there again, on those engines, last carbureted, you know, you're talking about early 80s. And afterwards, well, actually, in 1988, when we bought the Festiva race car, it was carbureted. But by 1990, that was it. The smaller the car, the smaller the engine, the easier it is to meet emissions, so you can stay with the cheaper technology longer. But eventually, you know, it was hopeless to really meet. Once they said you've got to meet it for 150,000 miles, you're going to have to rebuild this carburetor. And it's possible to get the fuel injectors and everything to where they don't need rebuilding for the last thing. It's just durability, and that's a much different part of automotive research. The problem there is this has to last 150,000 miles. How do we simulate that? The engine at Matthews building for the landfill project, that's the whole purpose of the engine is to solve that. How can we rapidly determine what deposits are going to be created here without putting in a 15,000-pound diesel engine and running it for 6 months or a year? So those also create problems, and patentable work that is very valuable. You know, as I said, I got a phone call when I was driving over here today. I haven't answered it yet. Back from the venture capitalists again. The last talk was we got the $5 million. It's ready to go. Pull out the trailer, run on the simulated landfill gas, and the money's yours. What does yours mean? You know, how much of this we got? Because they want to go public, and how much has to be spent for going public? You know, because if you're going to spend $5 million going public, we don't get anything. You know? So you know, if it only costs $3 million, and you're going to take $1 million, and we're going to take $1 million, that's great. So, but you can't discuss those details until you actually have the thing in front of you. You know what I mean?
Yeah.
It makes nobody really gets down to the last specifics of a deal until they know that it's a go ahead. And for non-engineers, that means you have to have a prototype. If you're dealing in a venture capitalist, these guys are not engineers. Trust me. They called up and had us do an analysis of a guy from Europe who had a perpetual motion machine. And he had hidden batteries in it, and it was basically an electric motor. He says, watch, and he spins it and it just keeps going. And the only spot in it you can put a battery, we said there's a battery there. And they checked, they go, oh gee, thank you, well, this cost them about $5 grand to find this out. You know, I mean, I just, if you believe in perpetual motion, I don't know what to do about you. You know?
And they have $5 million to give you?
Yeah, no, and that's nothing to them. Believe me,
How
that's
are they
nothing.
doing that well if they don't even understand
The California venture capitalists have made so much money on a few, you know, they make bets on broad range of things and hope one of them turns into Facebook, which is now in a lot of trouble, and then they start losing their money again. But this is somebody else's?
That's Camille, so I can take it.
Oh, okay.
You said engine is more likely to knock at low RPM?
Yes.
Why?
The reason the problem is low RPM, because remember, if you bring the temperature of the gases to a high and a high pressure, if they stay too long, it knocks. But at low RPM, the whole cycle is longer. So, yeah, I can take you out in my truck. I have no knock sensor, and just by launching at about 600 RPM and stopping on it, you can hear knock. Now, it's no problem. I've got forged pistons. After those broke up, I decided, let me build one that's maybe a little more than 300,000. So I got some real nice Weisco forged pistons, and I've knocked the living daylights out of it, and nothing's happened so far. All low-speed knock. You know, I mean, it's a cheap engine. The original cylinder block was in a 1979 Mercury that's in my truck now.
Yeah.
And we bought the whole car for $1,000. I had a graduate student. He came here from California. He had no car. I said, here's $1,000. Go buy a car. When you're done, give me the car back. And it had the same 2.3 liter engine that I ended up in 1996 buying one. So when it spit its pistons at 300,000, I rebuilt it with a set of forged pistons, just kept it. You know, the problem is it's a 1982 cylinder head that's also worn, and I need to rebuild that, and I haven't got around with that yet. So it's about 90 horsepower now in a 3,000 pound truck, and by the time I get to rebuild it, it'll be about 120. But that's what you need with a carburetor to get 27 miles per gallon. You know, it's the more underpowered it is, the higher on the performance map we operate with normal operation. As the engine gets smaller, the same performance map, we move up the map, right?
Yeah,
You got the same amount of torque at RPM to go 30 miles an hour,
More
but
miles
now
per
with a
gallon.
smaller displacement, we're farther up the map. Well, I'm pretty far up the map, because you know it's a 3,000 pound truck and it's got 140 cubic inches. It's not a high performance vehicle at all. But you could have got a 4 liter engine in it, 4 liter V6, 3 liter V6, and I took the 2.3 liter 4-cylinder.
Yeah.
Because I already had a block for it. I figured someday this was going to do the same thing, and it did. At about the same, the 1979 engine and the 1996 engines both coughed their piston at 300,000 miles, which tells me somebody at Ford says, we got to go 150, we got a 2-to-1 safety factor, because the other car that the graduate student bought and then gave back to me when it was done, it was high mileage when he bought it. It was like 100,000 when he got it for $1,000.
Yeah.
It was high mileage when he got it. We don't know how that guy drove it or whether he changed the oil or anything, but they both went. It's a fatigue on the thrust side of the piston, and that many cycles, and it quit. And that's pretty slick designing. You know what I mean? You know, that's why I was going to write him a letter and complain and see if I can get some. See if the people in the complaint department say, "What are you, crazy?" or you know. No, I write a letter say, you lulled me into thinking it wasn't going to break. This car went 20 some odd years and treated me nice, and now all of a sudden, out of nowhere, when I don't expect it, look at these pistons. Can you believe this? And see what I got, but I never got around to doing it. But it's still time. I got the pistons, you do that when I'm sure I'm not going to do business with them again in case they really do business. So, I don't think they would. The engineers would just laugh, but the people in the complaint department might not. Okay, if there aren't any other questions, then that's about.